Space is the ultimate frontier, a place full of endless possibilities and mysteries that have intrigued humanity for ages. From the vast sounds that fill the cosmos to the very start of time, come with us on a journey as we delve into the puzzles of the universe and contemplate its future. We'll go back to the beginning of the universe, observe its evolution, and peer into the distant future. We'll explore the limits of the cosmos and ponder whether there is truly an edge to everything we understand. The universe is extremely big, and there's this deep mystery that we don't quite get. It makes us think and question things. The mystery is about what's outside the universe. As we travel through space, we realize that what we can see is only a small part. What's outside these limits is still a mystery, a kind of cosmic curtain hiding the secrets of existence. Thinking about what's beyond is a bit like a deep question in philosophy. How do we understand things that we can't see or know? It's a tricky puzzle that makes us really think, sparking our curiosity and motivating us to find answers. Everything we can see, whether it's inside a room or the faraway galaxies visible through really big telescopes, is part of what we call the observable universe. Right now, the observable universe's limit is about 46.5 billion light-years away. But here's the puzzling part. The universe is only 13.8 billion years old. How does that work? It all has to do with the universe expanding. Because of this expansion, the places where the light comes from are moving away from us. So, even though the universe might be infinite, we can only see up to about 46.5 billion light-years because of this expansion. This boundary is like the edge of our universe. Now, think of it this way. When we look at the night sky, we don't see it filled with stars everywhere. That's because light has a limit to how far it can reach us on Earth. It's like there's an invisible barrier around us, and beyond that, there are billions more stars and galaxies. This barrier is called the particle horizon. There's also something called the event horizon, but it's different. The particle horizon marks the distance from which past light reaches us, while the event horizon is about the distance from now to an observer in the future. But there's another limit beyond these horizons called the Hubble horizon. If space objects are beyond this boundary, it's impossible for us to see them, even after billions of years. They're constantly moving away from us at the speed of light. So it seems like the universe has a limit, but it's really just the limit of how far light can travel. Think about it this way. When we look at bright cosmic objects, the light from them doesn't travel super fast. For example, the sun is 94 million miles away, and it takes 8 minutes for its light to reach us. Another star, Proxima Centauri, is 4.2 light-years away, so it takes about 4.2 light-years for its light to reach us. This means we can only see things that happened a certain amount of time ago. When we look up at the night sky, it's like looking back in time. Now, imagine a galaxy like HD1, which is 13.4 billion light-years away. To know what's happening there now, we'd have to wait the same amount of time for the light to reach us. Of course, this is if there are no obstacles, like black holes in the way of the light. If we could take a close look at this galaxy, we'd find out how our own galaxy formed in the early days of the universe. That's why studying light is so important for understanding how the universe has changed over time. This study helped us come up with the Big Bang theory. Now, after the Big Bang, there were some significant events, and those events left a mark. In the 20th century, astronomers like Penzias and Wilson discovered something interesting with their radio telescopes. They picked up a strange signal coming from all directions with the same strength. It turned out to be a leftover from the first light that appeared in the universe, a kind of cosmic microwave background radiation. In the early stages of the Big Bang, things were super hot. At that time, atoms couldn't form because electrons and protons couldn't stick together. The high temperature scattered or absorbed photons, which are tiny particles of light. So, light couldn't travel very far. It was like the universe was a dense fog back then. But around 380,000 years later, things started to cool down. The first stable atoms showed up, making the cosmos clear, and light could travel freely for long distances. This light, with a temperature above absolute zero, minus 454 degrees Fahrenheit, is what we pick up as microwave radiation. You can see it from Earth in any direction, even though it's coming from a whopping 13.8 billion light-years away. That's why scientists think the universe is the same age in years, although it could just be the limit of what we can see. Now, here's the tricky part. You can't see this cosmic microwave background, or CMB, with your eyes. The first light's intensity is really low because of the universe expanding. We'll talk about that later, but basically, the stretching of light waves makes them weak, and they end up in the microwave part of the spectrum. Even though it's not super powerful, the CMB is like a peek into the universe's early days, giving scientists a snapshot of the past. Thanks to the LHC, we now understand the Big Bang and how the world has been shaping up from its very start. Imagine the sky's map showing temperature changes of relic radiation like a pattern of spots. The blue areas are cooler than average, and the orange ones are warmer. These spots help scientists study how stars and galaxies have evolved because they show where the density changes, also known as seeds of structure formation, have taken place in the cosmic microwave background. The bigger spots, covering 1 degree in the sky, support the idea that the universe is flat. The smaller spots give loads of info about the universe's makeup and age. Studying the temperature features of the CMB is like another confirmation of dark matter and dark energy. Back in 2003, astronomers led by D.N. Spagel discovered that the amount of dark matter and dark energy is way more than regular matter. According to recent measurements, dark matter makes up 26.8%, dark energy is 68.3%, and ordinary matter is just a small part. Lastly, the CMB also told scientists how fast the universe is expanding, about 42 miles per hour per megaparsec. The CMB gives modern science lots of info about the early and current universe. It's like a guide to understanding what might happen in the future. The SMV and the space horizon both limit what we can see from Earth. Now, let's dive into what space horizons are and if we can peek beyond them. We talked about the cosmic particle horizon, which is like an imaginary line setting a limit to what we can see in the universe. It's a boundary based on the distance light from the past can travel to us. If cosmic objects are far beyond this horizon, we can't see them now. But guess what? There might be a way around this limit in our space exploration. Even though our particle horizon isn't fixed and light keeps traveling over a super long path, we usually need special tools to see more objects. Still, we can't see what's beyond this horizon directly. But here's an interesting twist. Enter the neutrino. It's a tiny particle with almost no mass and hardly interacts with matter. This means it can travel really far, almost at the speed of light. Neutrinos form during various cosmic events like nuclear processes in stars or supernova explosions. Even if these events happen hundreds of billions of light-years away, neutrinos can bring data about them to Earth. What's cool is that neutrinos can change into particles with even less energy during their journey. Because neutrinos are so hard to detect, scientists have been working on improving detectors. In the future, these tiny particles might help us learn about what's beyond the cosmic horizon. Besides neutrinos, there's another way for us to explore the universe beyond what we can see. It's through gravitational waves, kind of like ripples in time, caused by big things like black holes, neutron stars, or stars spinning around each other. When these things move, the waves they create travel in all directions at the speed of light. They can mess up smaller objects a bit and slightly stretch the space between them. By the time these waves reach Earth, they're not as strong, so they're not a threat. But, just like neutrinos, they're tricky to spot. The leftover ripples from these waves tell scientists what happened outside our visible universe and how far away it happened. For example, in 2016, scientists from MIT detected the collision of two black holes 1.3 billion light-years away using gravitational waves. These waves, along with neutrinos, act as guides beyond our limited view of the universe. Improving our technology to catch them is the key to understanding the entire universe. No matter how much we try to learn about the secrets of the cosmos, there's a big obstacle. Right now, we can't directly see stars and galaxies in the invisible part of the universe. Here's why. After the Big Bang, the universe kept expanding. Even though it slowed down a lot, everything in space is still moving away from each other. Every 326 light years, this expansion speeds up, especially because of something called dark matter, which is all over outer space. The particle horizon is also getting bigger as the universe expands. The larger it gets, the more objects that were beyond it start showing up on our star maps. But here's the catch. All the stars and galaxies we see now will never go beyond the visible space boundary. In the far-off future, we might see objects that are close to us now, and some of them, like the SMB, will look like faint dots in the night sky. However, because of the same expansion, many faraway objects will move away so fast that we'll never be able to see the light they emitted. The expansion of the universe also affects another limit called the space event horizon. This sets a boundary for any signals sent out, and anything beyond this limit will never reach the receiver. Right now, this limit is about 16 billion light years, so even if a galaxy is within one particle horizon, if it's beyond the event horizon, we won't be able to interact with it. As time goes on, a signal sent from Earth, for instance, will get longer and longer until it reaches frequencies we can't detect. The object that sent the signal will also be moving away from Earth, making it impossible for us to reach possible extraterrestrial life if it's too far away. Moreover, in the far-off future, even the galaxies we can communicate with might become too far for us to reach. The expansion is shaping the size of this horizon. In the past, it reached about 60 billion light years, but now it's down to 16 billion light years. In the future, this distance might get even smaller, leaving us in our space bubble without the chance for communication and scientific development. Adding another limit to our space bubble is the Hubble horizon. This is like a theoretical point about 14.5 billion light years away from us. Beyond this point, space objects move faster than the speed of light. The farther a light-emitting object is from this horizon, the faster it seems to move away from us. For a photon, it's like a race. The farther it is from Earth, the faster it moves away. Only beyond the Hubble limit will Earth stop accelerating. The Hubble horizon is also getting bigger, so with time, distant light can reach our telescopes. In the future, we might see more traces of galaxies and stars beyond this limit. But here's the catch. In the very far-off future, the Hubble horizon will collapse and shrink. It will stop around the galaxies of the local group. After that, no light from other cosmic bodies, unlike the light that has already gone beyond, will ever reach our cosmic horizon. We'll be cut off from the entire universe. But there's more. The event horizon and the Hubble horizon will come together in about 10 billion years, creating a new horizon with a radius of 63 billion light years. After that, we won't be able to see any events beyond this new boundary. After tens of billions of years, all light emitted beyond this limit will vanish forever. Even though humans are super curious, the universe has its own limits to keep its endless secrets. Picture these spherical horizons around us. They stop faraway light from reaching Earth, making it hard for us to study how our universe changes. What's more, in billions of years, these horizons will come together, blocking light from beyond Earth and stopping us from learning more about the vast universe. But here's the interesting part. Our technology is growing fast. In the future, we'll gather more and more data about deep space, thanks to things like neutrinos and gravitational waves. And later on, we might even create new horizons on other planets to explore. So, while the universe has its limits, our technology is helping us peek into its secrets. While we can't eliminate these limitations, we can handle them. It will take many more generations before we can go beyond our own horizon. But once we do, there will be countless other horizons to explore. All that's left is to be patient. Since the beginning of our existence, we've gazed at the sky and wondered about the vast universe. We've counted stars, mapped constellations, and imagined what lies beyond our small piece of the sky. But have we ever thought about the end? Not the end of our brief human lives, but the end of time itself. What will the final days of the universe be like? What will we see, hear, and feel in those last moments? Will everything end dramatically, or will something entirely unexpected occur? Throughout history, humans have thrived on exploring the unknown and pushing our understanding. Today, we begin the deepest journey yet, a journey to the very end of time. Think of each moment like grains of sand falling in an hourglass, bringing us closer to the inevitable end of the universe. But when and how will it happen? And what does it mean for us regular people? Imagine crossing huge distances in space and time, traveling billions or even trillions of years into the future. It's not about how far we go, but about exploring what will eventually happen to the whole universe, a journey to the end of time. Welcome to the Anthropocene, the age of humans. This is our time, our era. It's a period marked by the huge impact we, as a species, have had on our home, the blue-green sphere we call Earth. In the blink of an eye, we've shaped, manipulated, and forever changed the very fabric of our planet. Consider the Holocene, an era lasting 11,700 years, where human civilization took its roots. This era provided us with comfortable climatic conditions, allowing us to thrive from humble hunter-gatherers to modern, technologically advanced societies. It nurtured the birth of agriculture, writing, and the very concept of civilization. However, as we moved forward, the toll on our planet became clear. Our unending quest for resources and relentless expansion led to changes that signal the end of the Holocene. The weather is acting differently, with more extreme events happening regularly. The variety of living things on Earth is at risk. The balance that has helped us for a long time is in trouble. What we've done has made a lasting impact on Earth, bringing in a new time period called the Anthropocene. This part of Earth's story is written by humans. As we enter this new era, one big question comes up. What will we leave behind for the next generations? As we get closer to the year 2500, we see big changes happening on Earth. Our protective shield, the magnetic field, is shifting. The North and South poles are swapping places, something that last happened 780,000 years ago. This cool change is messing with our technology, making us adapt in new ways. Now, let's jump to the year 4385. We're seeing the return of an old friend, Comet Hale-Bopp. It's an amazing sight, lighting up the night sky with a bright trail of light. It reminds us how small we are in the universe. Fast forward to the year 5000, and we face a tough reality. Our past actions have caught up with us. The polar ice caps have melted, causing the sea levels to rise all around the world. Many coastal towns that used to be lively are now underwater, just relics of the past. In the year 6000, a huge asteroid is heading toward Earth. It's going to hit, and it will be a big, life-changing event. Fast forward to the year 8000, and something incredible is happening in the sky. A faraway star is reaching the end of its life and explodes in a stunning supernova. It's so bright that it outshines entire galaxies. This reminds us that the universe is always changing. As we watch the Earth and everything around it constantly moving in space, it makes us think about how everything doesn't last forever. When we look at the starry sky, we think about the challenges that are still ahead on our journey to the end of time. Fast forward 1 billion years, and our sun, the giver of life, starts changing a lot. It gets way brighter, making the Earth super hot. Temperatures go up, and the green carpet of plants starts disappearing, leaving empty landscapes. The air becomes thin, and we run out of the oxygen we need. The intense heat keeps going, and by 1.3 billion years, the huge oceans we had are starting to turn into vapor. Our once blue planet is slowly becoming a dry, brown place. The vast seas become just memories. Now, Let's go to the very end of Earth's story. In the 7.5 billionth year, the Sun turns into a red giant, swallowing up our once lush planet. That's the end of Earth. Our home, which took care of us for billions of years, is now going back to the cosmic dust it came from. Jump to the year 10 billion, and our Sun, after its fiery end, is born again as a white dwarf. It's not as strong as it used to be, just a faint, cool leftover from its earlier fiery days. Instead of raging nuclear fusion, it's now like smoldering embers, quietly watching the big cosmic show. Now, zoom to 100 trillion years later, and there's a deep quiet across the cosmos. The stars, which were like bright beacons, start going out one by one. They leave behind a really cold darkness, and the universe is in a kind of twilight. Fast forward to 1 quadrillion years after the stars are gone, and the universe gets colder. It started with the hot beginning of the Big Bang, but now it's heading into a cosmic winter. The universe slowly slips into darkness. The time of starlight is done, and the universe becomes like a big graveyard. What's left are the last bits of the stars that once lit up the cosmos. They glow with a faint, ghostly light, reminding us of the universe's fiery past. Around 10 quadrillion years later, these white dwarfs become the main things in the sky. This time is called the Age of Degeneration, where the universe is like a ghost, remembering the galaxies and stars that used to shine bright. It's a clear reminder of how things are born and die in the universe over and over. Even in its last moments, the universe keeps changing. Gravity, the force that shapes the universe, is still at work. It never stops. Gravity pulls stars and planets from where they're supposed to be, sending them into the empty space. Sometimes, these gravitational moves make new stars, and when they're born, they explode in really bright supernovas, echoing the past of the universe. Meanwhile, over trillions of years, white dwarfs start to disappear. They cool down, shrink, and their light fades until they vanish completely. When they die, these white dwarfs turn into black dwarfs. You can't see black dwarfs because they're invisible. They mark the time when the universe goes into darkness. This is the beginning of the era of black dwarfs. The universe, once full of light and color, is now just a shadow of what it used to be. The journey to the end of time continues in a universe that's getting colder and darker. As time passes, the universe keeps getting bigger and bigger. Every part of space is stretching, and even space-time itself is like stretchy fabric. What used to be an organized whole is now expanding endlessly, like many distant islands lost in a vast ocean. But in this vast space, something silent and big is happening. Protons, the tiny things that make up everything, start to break down. These protons, the heart of every atom, turn into ghostly neutrinos and photons. The stuff that makes up our world is falling apart. The universe is slowly wiping away the last bits of its physical history. All that's left are particles of light and black holes. At this point in the journey, the familiar things we know about how the world works are ending. We're heading into a new time in the universe, the era of black holes. Even the things that seemed like they'd last forever, the black dwarfs, have vanished. They gave up their mass to the ever-expanding universe. The last bits of stars have turned into cosmic dust. Now, black holes are taking over and becoming the main, if not the only, things in the universe. In this time dominated by black holes, the leftovers from once living galaxies, supermassive black holes, are super important. They were born when massive stars died or smaller black holes joined together. These huge celestial titans have grown to incredible sizes by sucking in matter and energy on a massive scale, way beyond what we could have thought. These big cosmic events send out gravitational waves, creating ripples in the fabric of space-time. Think of them as the last sounds the universe makes right before it ends, like the slow ringing of a bell echoing through the vast cosmos. Even these amazing things, like black holes, aren't as forever as they might seem at first glance. In the late 1970s, the well-known physicist Stephen Hawking came up with an idea called the Hawking radiation. This is how black holes lose energy and, as a result, lose mass over time. It happens because of certain things in quantum physics near the event horizon, which is like the edge of a black hole. Near this edge, pairs of particles and their opposites pop up. One of these particles gets pulled into the black hole, and this helps the other one to break free and escape into space. This whole process means the black hole loses energy and, therefore, mass. Over a really long time, this makes the black hole lose mass and get smaller. As this happens, the super strong pull it had slowly weakens, and eventually, the black hole evaporates. These events mark the end of the last big things in the universe, leaving behind a huge, seemingly endless empty space. Since the Big Bang, our universe has been getting bigger because of a special force we call dark energy. This mysterious kind of energy is thought to be everywhere in space and works opposite to gravity. It's making the universe expand faster. At the same time, there's something called dark matter, which makes up 85% of all the stuff in the universe. Dark matter pulls things together with gravity, kind of like a counterbalance to the expansion caused by dark energy. Right now, it looks like dark energy is the big player, but we should think about the possibility that things might change. Some theories say that as the universe keeps growing, more dark matter might show up, slowly making its gravitational pull stronger. If the pull of dark matter becomes stronger than the push of dark energy, the universe might start to slow down and maybe even go backward. It's like when you stretch a rubber band a lot, and then suddenly it snaps back. This process is called the Great Contraction, where the universe goes from stretching a lot to squeezing in on itself. This squeezing will make everything in the universe, like matter and energy, get really tightly packed. Eventually, we hit a critical point in this squeezing, the moment when everything is the most tightly packed and hottest. At this extreme point, the usual rules of space and time get all mixed up. This super tight and hot point is called a singularity. It's here that another Big Bang might happen, leading to the birth of a brand new universe and starting a whole new cycle of existence. This journey helps us understand where we fit in the universe. We see that our time here is short in the big timeline of the universe. Going on the journey to the end of time takes us back to the very start. Maybe, in a universe full of endless possibilities, the end is just another way of beginning. Many times, you've probably thought about what will happen in the future, maybe in 100,000 or even 1,000,000 years. Just for you, we're trying to peek into the future by looking at how the stars in the night sky evolve. Today, we'll try to understand what our universe will be like in 100 million years. Fasten your seatbelts, and in a few seconds, you'll go from the very start of the universe's life to its last moments. Our journey is about to start. Certainly, nothing in our universe lasts forever. In the next 100 million years, all the big stars we see in the night sky will vanish. Instead, there will be fields of nebulae. Stars begin as large clouds of gas and dust. They change over tens of millions of years and then stay bright in space for millions or even billions of years. Stars, despite not changing much during their lifetime, eventually start dimming and shrinking due to the synthesis of hydrogen into helium. The end stage begins, which lasts a bit less than their actual life. Stars similar to the Sun, after about 9 to 10 billion years, become red giants. After billions more years, they completely fade away, leaving behind only bits like white dwarfs and a mix of gas and dust from which new stars can be born. However, the next 100 million years will also have an impact on our Sun. It will get brighter and warmer by 1%, and in 1 to 2 billion years, it will heat up to a point that could be dangerous for life on Earth. But what if we could slow down this process? Even though 100 million years is an incredibly long time for humans, our science might advance to levels that seem like science fiction to us now. In 100 million years, we might be able to control the stars and decide how long they will shine, thanks to stellar engineering. During this time, humans could theoretically replenish a star's fuel or control its nuclear reactions artificially. This way, the sun could last longer without threatening life on Earth. Manipulating stars might also create conditions for life on planets that we currently think are uninhabitable. In the future, humans might even be able to extract hydrogen and helium from stars for energy production. As human civilization expands greatly, the resources from planets might not be sufficient to power everything for so many people. Using a theoretical Dyson sphere, which collects energy from a star up close, could save resources and the environment on planets where people might live. However, if we use stellar engineering to speed up star aging by collecting fuel, life near these stars could become risky. Certainly, it's not just stars that change with time. Galaxies do too. The one we live in formed at the start of the universe and is moving toward its end. Before galaxies die, they go through a long process of evolution. By merging with others over a long time, smaller galaxies become part of larger ones. So, in the next 100 million years, we might see fewer small galaxies, and the mix of spiral and elliptical galaxies could change a bit. Future humans might witness many galaxy mergers, especially with small ones, leading to new structures like wave tails and especially supermassive black holes. Our galaxy, the Milky Way, is also heading toward another galaxy, Andromeda. But no need to worry. Even in millions of years, their collision won't happen for about 5 billion years. In the next 100 million years, our galaxy will have moved around 978,000 light-years, but it won't affect us. After the same amount of time, galaxies will shift to areas with different densities, changing their shapes and how stars form. However, even the bright and beautiful galaxies of the future will fade. The reason for this is the death of stars, especially big ones that determine a galaxy's color and brightness. After a star explodes for the last time, most of its gas stays inside the galaxy, keeping it alive. Yet, some of it escapes, and this means fewer big stars form. The galaxy loses mass, and in millions of years, there might only be a black hole left in its place. Actually, finding anything that stays still in our universe is impossible. Everything is always moving, maybe even the universe itself. Since the very beginning, with the Big Bang, the universe has kept getting bigger. In the hot Big Bang phase, it expanded faster than light. Only when it cooled down and protons, neutrons, and electrons formed did it slow down a bit. Over 5 billion years, it slowed down a lot. But both now and in the future, the universe won't stop expanding. It's important to know that when we talk about expansion, it doesn't mean that things are moving like objects racing across space. It's more like time itself is stretching, similar to a balloon with 2 dots on it. The more you blow it up, the farther apart the dots get. However, this doesn't really affect things held together by gravity, like our galaxy and Andromeda, or even ourselves. The amount of regular and dark matter always stays the same. Only the space and the density of matter change as they spread out over a large area. Yet, we notice that other galaxies are moving away from us. In the next 100 million years, the galaxies in our local group might be so far that it becomes a bit tricky to see them. Distant galaxy clusters, like CLJ 1001 Plus 0220, will probably be almost invisible. But here's the catch. The universe is expanding faster and faster. The speed is increasing by 44 miles per hour, and every 3.26 million light-years, it gets even faster. This isn't great news for the universe. In millions of years, it might be tougher for cosmic bodies to form because the building blocks would be flying apart too quickly. The main reason behind this is dark energy, which could, in theory, work against the pull of gravity from matter. Dark energy is a kind of energy we think might exist, and it's a crucial part of time. It can have important effects in the future. In the next 100 million years, the speed of expansion might increase so much that galaxies stop coming together and change. The dust and gas thrown out when stars die will spread out, and new stars will form less often. Even worse, in billions of years, the gas leaking out might be so fast that nothing can form. No stars, no galaxies, and no life. This would lead to a thing called heat death eventually. The idea of heat death doesn't mean our universe will turn into a fiery hell through star evolution. It's about the future fate of the universe based on the second law of thermodynamics. This law says that in a closed system, disorder or entropy increases over time. It means that energy will spread out in a way that nothing can come together. Imagine a cup of tea. The heat leaves it and spreads into the room, making the tea's temperature the same as the room. So, it can't warm you up when you drink it anymore. In the same way, galaxies will be too far apart, and stars will fade because there won't be enough energy or matter for stars, planets, or other space things to evolve. Eventually, the universe will become completely dark and empty. Dark energy might not just lead to heat death in the future. If the universe expands much faster in the next 100 million years, it could face total death. In this scenario, stars won't just stop forming, they won't exist at all. Even basic particles won't be around. Unlike matter such as stars, which stays the same and doesn't increase its mass with expansion, when the expansion becomes really fast in a few billion years, stars won't handle the extra energy and will just explode. Another way our existence might end is called the Big Rip. This idea says that since we probably can't control the speeding up of expansion, in 200 billion years, it will get so fast that gravitational pull will break. Planets will wander off their orbits, and then the force that holds stars together won't be able to resist dark energy. With even more time, atoms might not resist and get torn apart. There's also a chance that, after the Big Bang, everything in the universe goes back to the first stages of the Big Bang. However, what stays in the singularity won't look like the hot and dense plasma at the start of the Big Bang. It'll be cold and thin. So, even though the hypothetical end of the universe sounds bad, there's a chance it could be a new beginning. There might be another threat to the whole universe, and it could be within us. We all know everything around us is made of atoms, and there are two tiny parts inside an atom's nucleus called a proton and a neutron. These particles are usually stable in the nucleus, meaning they don't decay. But what if that's not always true? The proton is a really common particle in the universe, and it can even exist outside the nucleus. The proton stays stable for some good reasons, like the laws of conservation of energy, charge, and baryon number. According to the standard model of physics, the proton shouldn't decay at all. However, newer theories, like the grand unification theory, which combines electromagnetism, weak and strong interactions, suggest it could happen. In the distant future, there's a chance that protons might decay. This process probably won't cause a disaster for the entire universe, but if it happens a lot, in millions or even billions of years, part of the universe might disappear. If protons start to decay, it can mess up the nucleus of atoms and create things from the decay that might affect the whole universe's structure. As matter breaks down, the system of how galaxies evolve in places where proton decay happens would get messed up. People in the future might have protons in their bodies decaying, but the danger within the next 100 million years, along with heat death and the Big Bang, could be even worse. If the collapse of protons is too big and strong, it might lead to a scenario where the universe meets a terrible end. But it's not just because of protons alone. Imagine all matter in the universe getting wiped out, leaving no trace of its existence. This might happen through a theoretical bubble. You've probably heard of the Higgs boson, a vital part of the Higgs field, a field that's everywhere in the universe. When particles interact with this field, they gain mass. The Higgs field can also affect what we call a vacuum. We usually think a vacuum is empty space, but it has quantum fields in it. A vacuum tries to have as little energy as possible. The Higgs field decides if the universe is in a true vacuum, stable with the lowest possible energy, or a false vacuum, which is less stable with higher energy. According to current theories, our universe is in a metastable state, meaning it's in a false vacuum. This is the danger for all future life and matter. In the next 100 million years, if a super-energetic event, like a huge proton decay, occurs, a tiny part of the universe might shift into a true vacuum state. This could create a bubble of true vacuum that expands at the speed of light, wiping out all matter and basic particles in its way. Life would struggle to appear in any form after such a catastrophic event. The universe we know will transform over time, becoming totally unfamiliar one day. It will keep evolving, but like all things, it will start to fade away at some point. We don't know exactly when this will happen, no matter how much we try to predict the future. However, one thing is certain: humanity will make several remarkable discoveries in the future. Maybe, in 100 million years, these discoveries will uncover the complete history of the universe and ourselves for the people of the future. The vast expanse of outer space, often referred to as the final frontier, is a captivating celestial canvas filled with stars, galaxies, and nebulas intricately connected by the cosmic threads of the universe. However, what happens when we encounter a break in this grand design? Picture a space where the cosmic loom appears to have faltered, resulting in an almost unimaginable vastness. Imagine an area so immense and empty that even if you were traveling at the speed of light, it would take over 330 million years to cross. This space is approximately 23 times larger than our own Milky Way galaxy, a desolate region with an incredibly low density of galaxies that challenges our understanding of cosmic structure. Remarkably, this is not a scenario from science fiction, but rather a genuine and mysterious aspect of our universe. Welcome to the Great Void, a cosmic enigma, an immense dark abyss that surpasses our comprehension of the universe and how it came to be. To truly understand our journey into the cosmic void, let's go back in time. Picture the late 1700s when astronomers first glimpsed the idea of cosmic voids. A new era of astronomy began with the invention of the telescope, allowing astronomers to map the cosmos more accurately. As they charted the vastness of the Milky Way, they could barely fathom the enormous cosmic structures beyond their view. Fast forward to the 1900s, where modern telescopes and advanced observation techniques revolutionized our view of the universe. Astronomers realized that our Milky Way is just one of billions of galaxies in an incredibly vast universe. When they plotted the distribution of galaxies, something odd emerged. Some areas had way fewer galaxies than expected. Initially seen as observational quirks, these areas later became known as cosmic voids. It wasn't until the second half of the 1900s that the idea of cosmic voids started to gain attention. In the 1970s and 80s, studies using redshifts, a method to measure galaxy distances, showed that the universe's large-scale structure wasn't random. Instead, galaxies seemed to create a kind of cosmic web, leaving vast, empty spaces in between. With the rise of digital technology and more powerful telescopes in the late 1900s and early 2000s, our knowledge of these voids expanded. Projects like the Sloan Digital Sky Surveys and 2DF redshift studies provided detailed 3D maps of the universe, giving us a better understanding of these cosmic voids. Exploring cosmic voids, from early hints by astronomers to today's advanced instruments, is a captivating part of our journey to understand the universe. However, even with our advancements, these huge empty spaces still puzzle scientists. The Great Void is a mysterious place. As we explore its secrets, we're curious about how it came to be. When astronomers closely examined the distribution of galaxies, they found an interesting pattern. Instead of being randomly scattered, galaxies on a large cosmic scale joined together to create intricate networks known as the cosmic web. This web includes clusters of galaxies, threads connecting these clusters, and big empty spaces in between. These voids stand out as huge areas with fewer galaxies, quite different from the crowded clusters and threads of the cosmic web. Understanding the big picture of the universe was a crucial step in figuring out cosmic voids. These voids aren't just empty spaces without galaxies, they're important pieces of the cosmic puzzle. Now that we've navigated through the cosmic maze and found these voids, let's explore one of the most mysterious voids we've confirmed so far. A void so big, it's called the Great Void. Welcome to the Bootes Void, named after the constellation it's in. Discovered in 1981 by astronomer Robert Kirshner and his team, it's one of the biggest voids we know of. How big? Well, it's about 330 million light-years in diameter. To put that in perspective, if you were traveling at the speed of light, it would take you 330 million years to cross from one side to the other. That's roughly 23 times larger than our Milky Way galaxy. Bootes Void isn't just huge, it's also super empty. In a space where we'd normally expect to find 10,000 galaxies, there are only 60 in Bootes Void. Imagine it like a cosmic desert, a vast emptiness in the midst of a densely populated cosmos filled with galaxies. The existence of such a massive empty space goes against the idea that, when looked at on a really big scale, the universe should look roughly the same in all directions. The mysteries of Bootes Void go beyond just being big and empty. For example, some galaxies in the void are oddly arranged in a tube-like structure, and we don't fully understand why. As we keep traveling through the cosmic seas, our next destination is another significant empty space called a supervoid. The one we're headed to is called the Eridana supervoid. It's not just a regular void, it's a superhollow. This colossal structure, named after the constellation it's in, is one of the largest things ever found in the universe. To help you grasp the enormity, this superhollow spans about 1 billion light-years. If you could travel at the speed of light, it would take an astonishing 1 billion years to go from one side to the other. The Eridana supervoid is not only massive, but also remarkably empty. While it's not as lacking in galaxies as Bootes Void, its vast space is still surprisingly empty compared to the galaxy-filled cosmos around it. What makes Eridana supervoid especially interesting isn't just its size or emptiness. This supervoid is connected to a mysterious cosmic happening called the cold spot of relic radiation. A cold spot of relic radiation is an unusually chilly area in the cosmic microwave background, which is the afterglow of the Big Bang. Some scientists suggest that this cold spot might be caused by the Eridana supervoid. The huge void could lead to something called the Sachs-Wolf effect, where photons lose energy passing through the void, creating a colder patch of relic radiation. As we keep going through the cosmic deserts, we stumble upon another vast emptiness. Welcome to the Canes Venatici supervoid. This supervoid, located in the Hound Dogs constellation, shows us just how huge our universe can be. Like other supervoids, Canes Venatici is in a space with a lot fewer galaxies than we'd expect. To grasp its scale, think about this. It's a whopping 1.2 billion light-years wide, around 8 times the size of our Milky Way galaxy. If you were traveling at the speed of light, it would take you over 1 billion years to go from one end to the other. In the midst of the lush forest of galaxies, the Hound Dog supervoid stands out like a cosmic desert, a deep, empty space. While the size and emptiness of Canes Venatici supervoid are intriguing, a big question remains. How did such a massive void come to be? What happened in the early universe to create this vast expanse of emptiness? While the precise process behind the creation of voids remains uncertain, various compelling theories have been suggested. One prominent scenario revolves around the idea of cosmic inflation. According to this theory, shortly after the Big Bang, the universe experienced a rapid expansion or inflation, stretching space itself. During this inflationary period, quantum fluctuations may have amplified on a cosmic scale, resulting in regions of higher and lower density in space. Over billions of years, matter was drawn towards the denser regions, forming galactic clusters and filaments, while the less dense regions were left behind, eventually becoming cosmic voids. The second idea involves dark energy, a mysterious force that makes the universe speed up. Dark energy might have influenced the creation of empty spaces by pushing galaxies from areas with fewer objects to those with more, essentially expanding these empty spaces over time. Additionally, the development of cosmic voids could be linked to large-scale processes in the universe, where matter and the universe gathered together due to gravity, forming structures like galaxies and clusters. In the remaining spaces, voids naturally emerged. The universe creates material structures around empty spaces. These theories represent just a few of the ideas scientists are exploring to understand the formation of these cosmic anomalies. However, as immense and enigmatic as these expansive voids are, they only constitute a fragment of the intricate cosmic puzzle that scientists are still working to piece together. Understanding the exact processes that result in the creation of voids is a challenging mission, as they remain shrouded in mystery. One significant obstacle arises from the vast scale and complex nature of the universe. The cosmos is vast, filled with innumerable galaxies, each with its own distinct properties. Comprehending the interactions among these galaxies and how they contribute to the overall cosmic structure is an enormous task. Adding to the complexity is the elusive nature of dark matter and dark energy, undetectable forces thought to be crucial in shaping cosmic structures and voids. However, our understanding of these forces is still in its infancy. The lack of a clear comprehension of what dark matter and dark energy actually consist of makes it challenging to decipher their impact on the formation of voids. Nevertheless, ongoing research in this field is dynamic and continuously advancing. Scientists are utilizing progressively sophisticated tools and techniques, spanning from cutting-edge telescopes to intricate computer simulations, as they strive to unravel the mysteries of these expansive empty spaces. Extensive surveys, such as the Sloan Digital Sky Survey, visually depict the distribution of galaxies across the universe, providing invaluable data for the study of cosmic voids. Meanwhile, computer simulations enable the recreation of the universe's evolution under varied conditions, aiding in the testing of theories about void formation and contributing to our quest to understand the origin of these vast cosmic voids. Each new discovery and every piece of data obtained bring us a step closer to unraveling the truth. The significance of these great voids extends deeply into cosmology, impacting our understanding of the universe and its structure. Firstly, they offer a distinctive perspective on the roles of dark matter and dark energy, two elusive yet dominant components of our universe. Dark matter, although unseen, serves as the foundation for the large-scale structure of the universe. Its gravitational influence contributes to the formation of the cosmic web of galaxies and voids. The very existence of these vast voids suggests that dark matter played a pivotal role in shaping the universe as we observe it today. Simultaneously, dark energy, the enigmatic force governing the accelerated expansion of the universe, may also play a pivotal role in the expansion of these voids. By propelling galaxies away from less dense regions, dark energy can cause the inflation of these voids over cosmic timescales. However, the significance of cosmic voids goes beyond their growth. Studying these voids can offer crucial insights to refine our current cosmological models and theories. For instance, the size and distribution of cosmic voids can serve as a unique test for cosmological models. If a model accurately predicts the properties of these voids, it confirms its reliability. Conversely, any disparities between model predictions and observations may indicate the necessity to refine or even develop a new theory of physics. In fact, these expansive cosmic voids, once perceived as mere empty spaces, now hold a significant place in our ongoing quest to comprehend the universe. But what if these voids are more than just empty space? Studying them has led to theories that go beyond our familiar universe, venturing into the realms of speculation and the extraordinary. One such theory involves the concept of alternate universes, or a multiverse. This idea suggests that our universe might not be the only one, but one of many universes existing in parallel to each other. According to some theorists, these great empties could potentially be more than just vast spaces of emptiness. They could be interfaces or gateways to these alternative universes. This assumption is rooted in certain interpretations of quantum mechanics and string theory, which propose the existence of other dimensions beyond the three spatial dimensions and one temporal dimension we encounter. If these dimensions exist, they could potentially contain many alternative universes, each with its own set of physical laws and properties. It's essential to note, however, that this idea is highly speculative. While it offers an intriguing perspective and has inspired countless science fiction stories, it's far from being widely accepted by the mainstream scientific community. To date, we have no concrete evidence for the existence of alternate universes or other dimensions. Moving on, let's revisit the idea we talked about earlier, the idea that connects the vastness of the universe with the tiny quantum world. This concept is all about quantum fluctuations in a quantum sphere, where particles and energy constantly appear and disappear, creating a frothy sea of fluctuations. But how do these tiny happenings relate to the enormous cosmic voids? The answer takes us back to the earliest stages of the universe's development, right after the Big Bang. During this time, the universe was incredibly small and hot, and in such a state, quantum effects could have a big impact on the cosmic scale. Quantum fluctuations that occurred then might have become more intense as the universe expanded. These amplified quantum fluctuations could result in an uneven distribution of matter and energy. Over billions of years, regions with lower density could turn into the vast cosmic voids we see today. In this scenario, the great voids are like ancient imprints carved onto the fabric of the universe by quantum fluctuations in its earliest moments. Confirming such a theory is a tough job, needing precise measurements of the large-scale structure of the universe and a deeper grasp of quantum physics and cosmology. Yet, the idea of connecting the smallest scale of the quantum realm with the largest scale of the cosmos is tempting. Another captivating hypothesis takes us into the complex and abstract world of topology, the math study of space and its properties. In the universe, topological anomalies or space defects refer to irregularities in the fabric of space-time, similar to defects in fabric. These defects may represent areas where the normal structure of space-time is disturbed. But where could these anomalies have come from? To answer this question, we have to go back to the inflationary period of the universe, just a fraction of a second after the Big Bang. During this superfast expansion phase, the universe grew a lot. While this inflation made the overall distribution of matter and energy more even, it might also have magnified tiny irregularities in space-time, creating what we call topological defects. These defects could then act as spots where matter couldn't easily gather, eventually leading to the vast empty spaces we know as cosmic voids. To understand cosmic voids better, we need to look at one of the most mysterious things in the universe: black holes. Specifically, we're talking about primary black holes. Unlike the black holes we're used to, which form from the collapse of massive stars, primary black holes are thought to have formed shortly after the Big Bang. They might have been created by extreme density fluctuations in the early universe. Now, you might be wondering, what's the connection between these ancient black holes and our cosmic voids? Well, one idea suggests that these voids might be full of what we call primary black holes. According to this thought, the large voids we see might be because there are a lot of these primary black holes hiding in these areas. Since they don't give off much radiation, it's tricky to spot them directly. But their presence has a gravitational effect, essentially clearing the space around them and adding to the vast emptiness we observe in the cosmic world. Another theory links the story of how the great voids came to be with the mysterious dark matter. Even though we can't detect dark matter in the usual ways, it's believed to make up about 85% of the universe's matter. Dark matter plays a crucial role in building cosmic structures, creating a huge connected network that links galaxies together. These strands of dark matter, called filaments, act as a support system for the universe, guiding the formation of galaxies and galaxy clusters. But what if something could disrupt these threads? What if a huge event or an unknown force could make these threads collapse or break apart? That's where cosmic voids come in. According to this theory, if strands of dark matter collapse, it could create these massive empty spaces. The collapse of these filaments would mess up the flow of matter, leaving behind large empty expanses. As we've learned, these huge empty spaces are far from being barren lands. They hold a treasure trove of clues and mysteries about the universe and what it's made of. From understanding how the universe's large-scale structure forms to figuring out the behavior of dark matter and dark energy, the mystery of the Great Void challenges our ideas about the cosmos. We might not have all the answers yet, but every question we ask and every void we explore gets us closer to unraveling the mysteries of the cosmos. And remember, every time you gaze up into the night sky, you're not just seeing stars and galaxies, but also invisible cosmic voids. These silent guardians of the cosmos continue their eternal watch, holding the secrets of the universe in their vast spaces. About 13.8 billion years ago, there was a singularity, a super-dense and super-gravitated entity. It rapidly expanded and cooled, giving rise to our universe. This event is called the Big Bang, but speculating about these things doesn't give us answers. It just creates more questions. What was there before the Big Bang? Is there even a before in a universe where time itself started with this explosion? Are we in the last part of an endless cycle of cosmic death and rebirth? Some brilliant minds have suggested theories, each as mind-boggling as the next. Some talk about other universes, while others imagine a universe that breathes, collapses, and expands in a never-ending cycle. Let's try to make sense of what actually happened before the beginning of time itself. Imagine a universe that breathes. It expands out from one point, grows for billions of years, and then shrinks, pulling in all matter and energy. This is the main idea of the oscillating universe theory. In this model, our universe is just one part of a never-ending cycle of getting bigger and then smaller, a cosmic dance without a start or finish. Each cycle begins with the Big Bang, a powerful moment of creation. After that, there's a long period of expanding for billions of years. This expansion slows down, stops, and then turns around. The universe starts contracting, leading to the Big Crunch. During the Big Bang, galaxies collide, stars get squished, and all matter and energy squeeze into a single point with infinite density, pretty much like the singularity where the Big Bang came from. But this isn't the end, it's the start of another cycle. The singularity bursts out with another Big Bang, kicking off the next round of the universe. In this model, each universe could last for billions or even trillions of years, and every Big Bang sets the stage for the next one. It's a captivating idea, like a cosmic pendulum swinging between making universes expand and then contract, destroying and recreating them. However, the theory of an oscillating universe has its problems and critics. We're still figuring out many things about how the universe expands, the exact energy makeup, how gravity acts on these scales. The data we've gathered from the cosmic microwave background suggests an ever-accelerating expansion, not a possible future contraction. But, as always, science is always changing. Ideas that were once rejected might get a new chance with new discoveries. As we explore space and time, we've always seen our universe as special, a single bubble of reality in a vast sea of nothingness. But what if we're not alone? What if our universe is just one of countless others, each with its own rules, history, and start and end? That's the idea behind the multiverse theory. Imagine a huge cosmic ocean where many bubbles pop up and vanish. Each bubble is like its own universe, and ours is just one among many in this cosmic foam. Some universes might be different, with unique physical laws or even other dimensions. Others might be quite similar, maybe even hosting life like ours. What if some of these universes existed before ours? Could our Big Bang have happened because of a connection with another universe? The multiverse concept challenges how we see our place in the cosmos, but it's a theory full of speculation. While it's fascinating, it's also controversial. If these other universes are beyond our reach, how can we find or study them? If the theory can't be tested, is it even scientific? Despite these questions, physicists are still researching and debating the multiverse theory. It's at the edge of our understanding, where science meets philosophy and observable facts lead to deep questions about the nature of reality itself. Despite the idea of many universes with various physical forces and dimensions, let's get back to our reality. Our understanding of the universe is based on two main ideas from modern physics: quantum mechanics, explaining the tiny atomic world, and general relativity, explaining the vast world of large dimensions. But what happens when these two worlds come together? According to Einstein's general theory of relativity, space and time are woven together into a four-dimensional fabric known as space-time. Massive objects distort this fabric, creating what we feel as gravity. On the other hand, quantum mechanics presents a world where particles can exist in multiple states at the same time, appearing and disappearing, a world that challenges our everyday logic. These two theories meet at the singularity of the Big Bang and in the center of black holes, where the scales of quantum mechanics and gravity come together. Scientists have long sought a theory of quantum gravity to blend these conflicting views. One exciting idea from this search is the no-boundary proposal, supported by physicists Stephen Hawking and James Hartle. According to this theory, the universe didn't start from a singularity. Instead, space and time are finite but limitless, similar to the surface of the Earth. Just like you can travel around Earth without falling off the edge, you could move around the universe without hitting a boundary. In this idea, the universe would be like a four-dimensional sphere, and the Big Bang would be a smooth point, kind of like Earth's North Pole. But it's not a singularity. In this model, asking what happened before the Big Bang is like asking what's north of the North Pole. It doesn't make much sense. This approach helps avoid the problem of a singularity at the start of the universe. Like the other theories we've talked about, the no-boundaries proposal isn't perfect and has its critics. Still, researchers are studying it to bridge the incredibly large and incredibly small, pushing the limits of our understanding of how the universe began. Now, let's explore the world of string theory, a theoretical idea where the basic building blocks of the universe are not tiny particles, but tiny strings. These strings can vibrate at different speeds, and these vibrations create various particles like electrons, quarks, and photons. It's like these strings are playing different musical notes. But string theory goes further. It suggests there might be more than the three dimensions we're used to. These extra dimensions might be squeezed or hidden from us, but they still have a big impact on how reality works. In the context of our topic, one version of string theory, known as the pre-Big Bang scenario or the egg periodic model, proposes that our universe might have formed from a massive collision between two multiverse worlds or brains. So what happens after this collision? The two brains hit each other, bounce away, and then come back together due to gravity, colliding once more billions of years later. This collision might create another universe. So, what was there before the Big Bang? In this model, it could have been another universe like ours, existing on a parallel brane. However, string theory, while elegant and able to bring together quantum mechanics and gravity, lacks solid evidence. As we already know, proving such things is very tough. But what if we take a different approach? Instead of searching for a universe before ours, what if we reconsider the idea of nothingness itself? When we hear vacuum, we usually think of complete emptiness. But in the quantum mechanics world, the vacuum is far from empty. It's like a bubbling soup of particles and their opposites, popping in and out spontaneously. This is called vacuum fluctuations. The vacuum fluctuation model, or quantum fluctuation model, suggests that our universe might have started from one of these fluctuations. Imagine a tiny bubble of false vacuum that blew up into the universe because of quantum mechanics. This bubble, triggered by a phase transition or quantum tunneling, would start expanding fast. The negative pressure inside it would push its edges outward. In this bubble, the false vacuum energy could turn into matter, giving rise to stars, galaxies, and eventually, you and me. So, what was there before the Big Bang? According to the vacuum fluctuation model, it could have been a quantum vacuum, a sea of short-lived particles and their opposites. And our universe was like a random bubble that managed to grow into something much bigger. Although the vacuum fluctuation model is fascinating, it brings up challenging questions. For instance, why did this specific bubble get bigger while others didn't? And how do we make sense of the thought of a never-ending quantum vacuum when our universe seems to have a certain age? But as we explore the realm of quantum physics further, we discover even more interesting possibilities. One possibility in the field that mixes quantum mechanics with cosmology leads us to the next idea: the Big Bounce theory. Picture a universe that stretches, then squeezes, and finally bounces back like a rubber ball. That's the basic idea of the Big Bounce theory. Instead of a singularity where all the laws of physics break down, this theory suggests that our universe might have started from the remains of an earlier squeezing universe. In this model, the universe doesn't get squished into a singularity. Instead, because of quantum effects, it shrinks to a very small size and then starts expanding again, leading to what we now call the Big Bang. Similar to the oscillating universe theory, this theory suggests a universe with no definite beginning or end. Instead, there's an endless cycle of stretching, squeezing, and rebirth, avoiding the singularities that cause issues in other models. However, unlike the idea of an oscillating universe, the Big Bounce theory focuses specifically on the bounce, the point when the universe shifts from getting smaller to getting bigger. So how does quantum mechanics play a role here? Well, on very small scales, where the rebound happens, quantum effects are believed to be important. Some theories suggest that the universe might use a similar quantum tunneling effect to bounce from contracting to expanding. But remember, this idea is very speculative and has significant problems, both theoretical and observational. Can we find evidence for a previous contracting phase in our universe today? Can we create a quantum theory of gravity that works in these extreme conditions? However, the Big Bounce theory has its issues. The physics of how the shrinking universe can return to normal is still being explored. Figuring out how this process can happen without breaking the known laws of physics is the main challenge for this theory. The Big Bounce theory doesn't quite fit into our usual ideas of time and causality yet. But, as always in science, there are other theories competing with it. For instance, our universe might have started from something we know but don't fully understand, a mysterious and powerful cosmic object called a black hole. Black holes are colossal entities in the universe formed when massive stars collapse. They are areas where gravity is so strong that nothing, not even light, can escape. According to the general theory of relativity, the center of a black hole is a singularity, a point where density becomes infinite and space-time gets extremely curved. But what if these cosmic objects are not the end but the beginning? Some scientists think that inside black holes, singularities could create new expanding universes. This means our universe could be like the inside of a black hole belonging to another parent universe. In this idea, the Big Bang is like a black hole singularity forming in the parent universe. The expansion of our universe is then compared to the inside growth of this black hole. So, what was there before the Big Bang? It might have been inside a black hole in another universe. Perhaps every black hole in our universe could create a new universe inside itself. But remember, this is just a guess, and it has some challenges. How can we check if this idea is true? Can we see any effects from the parent universe? And how does this fit with what we know about black holes and singularities right now? Loop quantum gravity, or LQG, is a theoretical framework trying to connect two big ideas in 20th century physics: quantum mechanics, explaining really small things, and general relativity, explaining really big things. In LQG, space isn't smooth, but made up of tiny loops, like threads in a piece of fabric. When applied to cosmology, loop quantum gravity, or more precisely, loop quantum cosmology, suggests a rebound scenario similar to the big bounce we talked about earlier. This means that instead of collapsing into a singularity, as the traditional Big Bang theory and general relativity suggest, the universe shrinks to a minimum size. Then, quantum gravitational effects kick in and counteract the contraction. After that, the universe bounces back and starts expanding again. This suggests that our universe might have gone through a series of expansions and contractions, each starting with a quantum jump. What existed before the Big Bang? According to loop quantum cosmology, it might have been another stage of the universe, the contraction phase that happened before the quantum jump. In this theory, the concept of a quantum bridge is really interesting. This bridge acts as a link between our universe and the one before it. Instead of a singularity, the universe goes through a quantum leap, shifting from contraction to expansion. This jump, this change from getting smaller to getting bigger, can be thought of as a quantum bridge from the old universe to the new one. It's not a physical bridge like we usually think of, but a phase in the universe's evolution guided by quantum gravity. So, what's on the other side of the Big Bang? According to Luke's quantum cosmology, the universe before ours is linked by a quantum bridge. Even though this theory gets rid of the singularity at the Big Bang and gives us a neat quantum explanation for how the universe evolved, it still has some tough challenges. But if it turns out to be right, it paints a fascinating picture. A universe with no starting point or end point, going through endless cycles of squeezing and expanding. While these theories are interesting, they mostly remain in the realm of speculation. Each theory has its strengths and weaknesses, and none of them has solid experimental evidence in its favor yet. As we get closer to understanding what occurred before the Big Bang, it's likely that each answer will lead to more questions. However, the beauty of science is found in the process of exploration and discovery. Researchers worldwide work tirelessly to study and improve these theories, and even exploring just one theory helps enhance our overall understanding. So, what happened before the Big Bang? Right now, we're not sure. But regardless of the answer, the search itself enriches our understanding and encourages us to keep exploring.